let me begin. That's also quick. Let me begin by thanking the organizers for the opportunity to give a mini course here in Warsaw. So I plan to talk about stuff related to Gibbs measures and hyperbolic systems. Hyperbolic systems here means, for the purposes of this particular talk, mainly a knot of diffeomorphisms, which Christian did not define in his talk, but they're going to appear anyway. Christian also mentioned that he was happy that there were students in the audience. I'm always happy that there's students in the audience, particularly because it gives me an excuse to make jokes about giving things out at the beginning. So my usual story is that you won't get much out of the talk, so therefore I'll compensate by giving you something. But on this occasion, I'll just say that if you don't like entropy, Gibbs measures, or hyperbolic systems, then the only thing I can offer is chocolate, which is what I'm going to do. I may not sustain you for an hour and 45 minutes, but otherwise, if you could open the packet and distribute it by some means around the audience, that would be good. Okay. What am I going to talk about? Well, I wanted to start off by giving a little historical, prehistory kind of background about where some of the terminology comes from. And so this is going to be a sort of prehistory. And it's the prehistory in statistical mechanics. You may ask, am I qualified to talk about statistical mechanics? The answer is resoundingly no. But let me say some things anyway to try to motivate things along. So the basic idea is that we're going to look at something called a lattice gas, a one-dimensional lattice gas. And so the main ingredients of these are you consider a finite set of sites, so whatever that means. And for our purposes, it simply means that we're taking the numbers 0, 1 to some large number n, maybe n minus 1. So maybe I'll write this as z over n z. Why not? And so the idea here is that we have a bunch of sites labeled 1, 2, 3, up to, would you believe, n minus 1. And the idea is that each of these sites, we're going to put some sort of particle, and this particle will have two different states, whatever that means. So maybe it has something called spin up or spin down, but for our purposes, it simply means there's two different possibilities of each one. And so these states are just labels that associate states. And these labels are just going to be -1 or +1. So far, so easy. And the thing I forgot to say at the beginning was that up until last night, I was typing up some notes to cover this particular lecture. And these notes are posted this morning on my webpage. And rather than writing down some rather long, complicated URL, which is hard to type, the easiest thing is just to Google my name, which is kind of not a very common name. And you should find my webpage, or alternatively, you will find information about small hamlets, small towns in the center of England called Upper Pollicott, Lower Pollicott, and Greater Pollicott, which is the union of the two, which is possibly more interesting for you to explore. Okay, so we have these states, and so therefore we're going to have some sort of configurations. So in particular, I allow up to x and -1. So I have all the possibilities I get either a -1 or a +1 on each of these sites, of which I have illustrated it not very well by one sort of example. So maybe this one would be +1. This one will be -1, this would be +1, blah, 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 and this would be +1. And so using higher arithmetic, the total number of configurations is going to be 2 to the n. So total number of configurations equals 2n. Excellent. So far, so very easy. And this model was introduced by Ising in 1925 in his PhD thesis. Which I presume was quite a good PhD thesis. And he was trying to find something to do with things called phase transitions, which I might say a bit more about in a minute, for which this particular model is particularly useless, but it's got some applications to ergodic theory anyway. So we have, so for any given configuration up here, we have something else. Well, there's some interaction between nearest neighbors. And so we do that. Let's assume a nearest neighbor. Interaction. I might at this stage make some joke about illegal immigrants coming to Britain from France, but probably that's not very funny in Germany. Sorry, in Poland. So then, in particular, the site xi, which is just going, sorry, the site I, which has a weight plus or minus 1, which write it the following way. So the sites I and I plus 1, well, they contribute some particular value. And so these contribute a number which I'll call j xi plus 1 to the energy. What's j? J is just some number which is fixed, which is positive, and for a given configuration like this, each of these numbers is either plus or minus 1, and so this value here is going to be either plus or minus 1, depending on the two numbers you're multiplying together. And in particular, the total energy, you just sum all these guys up. So for a configuration of this form, I just sum up all these guys, and I get maybe minus j times the summation over the pairs, that's I equals 0 to n when it's 1. And using some sort of made-up notation, that will be xi plus 1, maybe mod. So every guy interacts only with his neighbors, and he has some contribution like this. Something like that, yes. So this gives us an energy, and the idea is that we want to use this to define a measure on this space consisting of 2 to the n guys. And so this leads to what's called the Boltzmann distribution. And what's that? Distribution. So there's only 2 to the n, so it's a finite set of points. And so the measure we put is going to be on the configurations. So if we have a longer piece of chalk. So how does this go? Well, it's going to be a measure, so all measures should be given a letter m or mu, apparently. And so it's going to depend on some parameter I'll define in a minute. And so for a particular configuration in this family of 2 to the n guys, I associate weight, and it's going to be exponential minus beta times h of x. So when this is a big number, I guess, then this is going to be a small weight, and we'd like to make it a probability. So there's a normalizing factor, which I'll just call better than. So this is where beta is just some useful constant bigger than 0, frequently called universal temperature. That was a matter. And where z of n is just going to make it into a probability. It's normalization. Okay, so now we have a measure sitting on all these different configurations. What's it good for? Well, one of the reasons that this particular viewpoint became useful was because if one wanted to simplify these expressions, maybe the expression for z of n, where we're summing up all these contributions, then we can introduce a matrix, which is very simply e to the j beta, e to the minus j beta, e to the minus j beta, e to the j beta. So it's a 2 by 2 matrix just involving this constant here and that constant beta there. And it's called T because it's a transfer matrix. And it has eigenvalues. Let's say it has eigenvalues lambda 1 bigger than lambda 2. In the notes, which are on my webpage, this calculation of what lambda 1 and lambda 2 is done. But I think it's not so difficult. And then in particular, when you look at what happens as n tends to infinity, since looking at just 2 to the n different states, it's not that inspiring, then it's natural to look at the growth of this denominator. And then, so this will be equal to maybe the limit as n tends to infinity of the trace, whoops, wrong way around, 1 over n, the log of trace of t to the n. So you take the matrix, multiply itself together n times. That kind of looks at how these guys fit together. And then what happens is it's a trace because I'm assuming it's kind of periodic at the ends. And then in particular, not surprisingly, this will turn out to be the log of the top eigenvalue. So far, nothing mysterious. And this quantity is usually called the energy. Okay, and so that's all I was going to say about the statistical mechanics. It's all kind of easy. But a lot of these ideas inspired ideas in what used to be called thermodynamic formalism. In Warwick, I'm used to lecturing where they always put one of the screens at the front, so you students can have a board. This one is much better designed. And so in particular, hyperbolic dynamics. Go down a bit. Such as our old friends like shift spaces, which are just infinite sequences, maybe of plus and minus ones or something like that, or some finite alphabet. An old friend such as the Ruel-Perron-Frobenius operator, which is a sort of generalization of this rather more modest matrix, and also equilibrium and Gibbs measures, which morally are a bit like what happens to the Boltzmann distribution, and another old favorite, which is the pressure function, which corresponds to this value here coming from log of lambda 1. So these are the sort of prehistory of a lot of these kind of concepts. So if you didn't like that bit, it's fine. The good news is I'm going to move on now to anosoptophiomorphisms. The bad news is I don't have any more chocolate, but there were, I think, 76 pieces in the audience. That's less than that. And so unless someone is particularly greedy, and it's quite likely that I use this one here. Species. Oh, yes. Excellent. I'm sure it will work, yes. My walking up and down in a slightly manic fashion is not because I'm chalk and chalk, it's just my usual lecturing style. Oh, okay, so what I want to do is to move in the general direction of some proper sort of dynamical systems, hinged with a bit of ergodic theory. in some reasonable sort of context. And so in my notes, I talk about general hyperbolic diffeomorphisms, but I thought, hey, why don't we limit ourselves for the moment to anosmic diffeomorphisms? And the great thing about anosmic diffeomorphisms is that if you're not familiar with them, then they're quite simple to define and understand. And if you are familiar with them, it's kind of easy to see how they generalize to more general systems. So there's something there for most people. And so I will let myself use the following notation. So it said in my notes, let M be a compact Riemannian manifold. I think I should use the word close for once. And I'll assume that F from M to N is some sort of smoothish map. So it should be at least C2, but generally my maps tend to be C infinity. And I'll assume that it's anosmic, which means something. So in particular, it's going to mean that when I look at my manifold and I look at the tangent space to the manifold, then it splits into two continuous subbundles, which I will call ES and EU. I wonder if I'm going to draw a picture. And here is a picture of a manifold. All my pictures of manifolds tend to look a little like misshapen potatoes, except when they're tori. Tori I can sort of draw. And so here is my point X. My transformation is called F, so here's going to be F of X. And then the idea is that I have some sort of splitting. So maybe I'll use two different colors of the tangent bundle. So like that, then like this. And so this guy might be ES at the point X, and then this one would be EU at the point X. This would again be EF of X at U. This would be, don't get lost, and this would be, wrong color. This would be EF of X S. If I put the arrows in the right way, so this is going to be the stable guy, this is going to be the unstable guy. I noticed that ever since around about 2000, I use the word guy a lot. I think it's an Americanism, which is crept into my style. That's what we call it. Okay, so what's happening here is that there exists constants C greater than 0 and some lambda smaller than 1, with the property that with this particular splitting, I should say with these DF variant subbundles, like in the picture. And then in particular, if we look at what happens to applying the derivative of the map F at the point X, that's there, right, it's restricted to EX to S, then everything goes down by a factor of a constant over N. Thank you very much. I should take some home for England as well. And if I look at what happens in the unstable direction, I should go backwards. And so in that particular direction, yeah, it shrinks at some particular rate going backwards. So this is the N greater than or equal to 0, I guess, and the N greater than or equal to 0. So this guy is going to get longer, and this guy is going to get shorter. There you go. Okay, and I also want to assume, which I frequently forget to do, that F is an F is transition. So those in the last lecture, there exists a density limit. Okay, so that's just notation or a definition or some approximation. And let me mention some very standard examples. So the most standard example known to man is going to be the Arnold cat map. So let me just mention that one. Examples. And this is going to be on the torus, which I'll either write as T2 or I'll write it as T1 plus T1. For some reason that will become apparent in a minute. And here, T1 is just the one torus, which I'll think of as being complex numbers of absolute value equal to 1. May not be clear why I want to do that, but that's what I'll do. And then the game is that the first example is going to be the Arnold cat map. I'm always tempted to put an inverted comma between the L and the D, but since I know no Russian whatsoever, I'm not sure if this is a good thing to do or not. And the Arnold cat map is just the usual guide. So F of 2 points, say Z and W. So from the torus. So this is going to be F T1 plus T1 to itself. How does it work? Well, if I've written it as a linear matrix, it would work slightly better, but I haven't. I've written it in this way, so it's probably Z squared W ZW, which would correspond to the matrix 2, 1, 1, 1 if I'd written it as a linear thing. Okay, and this is well known to be a Nosov. It's a splitting, of course, which just corresponds to 2 directions, which were the eigenvectors of the matrix. And a third version of this perturbed in the sense of being not too far away, not in the sense of being dramatic in any particular way, is the following. So what I do is I take a parameter lambda, which is going to be some complex number whose absolute value is smaller than 1. I can do that, I think. And then I'm going to define my family of maps from T1 across T1 to itself, i.e. the 2 torus to itself. And the way I'm going to define that is I'm going to take a point on here, that is just 2 points on the unit circle. And then what I'm going to do is map this into something. But instead of just taking various powers, I'm going to do something that looks a bit more exotic. I'm going to look at Z plus lambda over 1 minus lambda bar Z. That's something. Multiplied by ZW. And I'm going to do Z plus lambda over 1 minus lambda bar of Z times hopefully just one thing, let's go to W. What's happening here? Well, what's happening here is that I've written it as a product of 2 circles in the complex plane because I wanted to slip in this notation. And this is an example of what's called the Blaschke product. And the great thing about Blaschke products is that they preserve the unit circle, hence my notation. So this is a family, a whole family of maps. And of course, if lambda is equal to 0, then it reduces to our old friend F above, the Arnold cat map. I wanted to introduce the second example because not in this lecture, but in the next lecture, I'll talk about the speed of mixing and resonances and some stuff. And it's nice to have very concrete examples which you can analyze, and this is one of them. The first one is also a very concrete example you can analyze, but the results are very boring. They're a bit more interesting for this example. Okay, and so in the title of the course, I talked about certain kinds of measures. And so this is my basic dynamics. I've got some transformation. It's hyperbolic, stuff stretches or contracts according to the according to the particular direction you're facing, which bundle you're in. And so what I'd like to do next is to introduce some measures. And so the kind of measures I'm going to introduce, I called Gibbs measures in the title, but for the purposes of the definition, it's slightly easier to talk about equilibrium states. So I might use the two interchangeably, but the actual definition I'm going to give is an equilibrium state. So if this is about Nosov diffeomorphisms, here I'm talking about measures. Okay, so the definition I'm going to give is the following. So we're going to find a nice invariant measure for the transformation, invariant probability measure. And this invariant probability measure is going to be associated to a function. So we're given a function on our manifold and we associate to that a measure. And this will be the equilibrium state for that. So given a nice function g, let's for the moment assume that it's continuous. Hold the continuous functions or smooth functions are a bit better, but let's just start with continuous functions. We can associate associate maybe add one or two F invariance probability measure. It's going to be a equilibrium state or equilibrium measure, or alternatively a Gibbs measure. Mu of g. And how is it defined? Well, it's defined to be the measure, a measure, and maybe more than one of them, if I'm just looking at continuous functions. It's a measure which has the property, I look at the entropy, so this is going to be the entropy of the measure. So it's a measure mu of g, which is F invariant, and it has the property that the entropy plus the integral of the function g with respect to the measure g is as big as it can be. That means that this quantity is equal to the supreme, if I look at all mu F invariant probabilities. If it's France, I put an A at the end, it isn't, so I won't. And this would be h of mu plus the integral of g mu. So I can look at all possible invariant measures, and hopefully some of them will have a larger value for the entropy plus the integral, and in fact that's the result. So in this particular case, the good news is that equilibrium states always exist. If you have a continuous function. Why is that? Well, it's because you're roaming around on T invariant probability measures, which is a compact space in the weak star topology, and the quantity you're looking at is semi-continuous, and so in fact it has to achieve its maximum. Some words like that. So they always exist, but in order to get uniqueness, you have to assume that the potential G is a bit better than that, and so let me just say that equilibrium states are unique. Measures states are unique if G was a Holder continuous function M. So I tend to write C alpha of M for Holder continuous function. What's the value of alpha? Anyone you like, really. I just mean Holder continuous function, i.e. Holder continuous. I'm sure I had some words of wisdom to say at this stage, but they are eluding me. Anyway, so given a nice, so we're actually going to be more interested in the Holder case because the results are nicer, and but we can actually get these measures for any particular continuous potential just by some messing around in some nice sort of way. Oh yeah, so I lapse sometimes into saying states instead of measures. This, of course, is some reference to the history of physics and mathematics or something. So it's equivalent to the state. So here I should have said measure, really, to be more consistent. Okay, so given any continuous or Holder continuous function, we can associate a nice measure or a measure. It's not clear it's nice yet. And so what can we say? Well, the thing we should always do after a definition is to have an example. And everybody's semi-favorite example is the SRB measure. So Sinai Warwick measure. Sorry. So S over B. So being of a certain vintage, I was at some lectures that Ruel gave at IGF in, I think, 1985. And prior to that, they always called Bowen-Ruel measures. And then he insisted they could have some chronological ordering. And so it became Sinai, Ruel, Bowen. So Sinai worked on the first case for Nossel systems, and then Ruel generalized it to axiomatic attractors, and then Bowen has some contributions later. Stuff and stuff and stuff, exactly. So why are these examples? Well, because we can choose a particular function g, which gives rise to these magic measures. So in particular, if we let g of x be some particularly nice function, depending on your definition of nice, I'll call it phi for some reason. And so what is it? It's going to be a function which is defined on my manifold. How is it defined? Well, it measures the expansion in the unstable direction as you apply the transformation. So its definition is that I look at minus the log of the absolute value, I guess, the determinant of the derivative of the map in the unstable direction, possibly evaluated at some point x somewhere, something like that. Whatever doesn't make sense. And so this is kind of like the infinitesimal, it's the expansion in the unstable direction. Maybe it's the expansion rate in the unstable direction. In one dimension, well, when each of these splittings is one dimensional, the picture looks much better, but otherwise it's going to be a determinant of measuring some volume stuff. And so what's the point of it? Why is it a nice measure? Well, the associated Gibbs measure, or equilibrium state, has nice properties. And in particular, this is going to be the so-called XRB measure. And amongst its many mercurial and entertaining properties, it's absolutely continuous. On unstable limits, on, well, maybe local unstable limits. Excellent chalk. Oops. On unstable limits. By which I mean something like this guy. I take a point x, and the unstable leads through the point x will consist of all those guys y, sitting inside the manifold, of course, with the property that the distance, this is presumably the Riemannian metric, f to the n y. It's the unstable guy, so it's going to help if they go in the right direction, I suppose. So there should be minus n's up here, minus 10. And so maybe I want that this thing tends to 0. So whoops, this is going to be less than or equal to epsilon. I've got to hide in the corner. Less than or equal to epsilon for all n greater than or equal to 0, something like that. So what does that mean? Well, it's just a piece of something about to become yellow. And so it will be some submanifold, not too long, sitting inside here. It's going to be W unstable epsilon of x. And then there's a measure which sits on the entire space, and it induces on this particular piece something that looks like the volume. In the special case that if F was area preserving or volume preserving, it could happen, but it typically doesn't, then mu of phi, the XRB measure, would be equal to the normalized volume. So it's a generalization of the volume in some sense. Okay, nothing has happened yet, which is fine. So we have null self-diffeomorphisms. It's probably for me. We have a null self-diffeomorphisms. We have a nice measure, the SRB measure, which we can think of as an equilibrium state, or we can just think of it as being the SRB measure, whichever we prefer. What I wanted to get to was how to construct these guys. So in particular, let's recall how to construct the SRB measure. So in the context that we're in, the context we're in is the context of a knot-off diffeomorphisms, where as a result of the Sinai, which dates back to 1968. I want to make some historical reference to 1968, but maybe I won't. And so we described a particular way to construct these things. So this is going to be Sinai's construction of the SRB measure, which I'll just call mu subscript phi. And his construction, which dates to the descent from 1968, was the following. What we do is we take lambda. So lambda is going to be a bit of volume. And this is going to be a bit of normalized. It's going to be a probability type volume. And it sits on this yellow curve, W, U, epsilon, X. So the hyperbolic splitting we see in the tangent space, but this piece of unstable manifold, which is kind of localized because of the epsilon, is just some like an embedded disk, or in this case, just an interval embedded into the manifold. And you can just set a volume on it. In my picture, it's one-dimensional. It would be like a one-dimensional volume, but that's fine. I don't need to be too specific. And then what we do is we move it around under the diffeomorphism. So what I'll do is I'll define a family of measures mu of n, and this will be an average, so it's 1 over n, the summation k equals 0 to n minus 1. And then it's going to be f, project notation, star the k of lambda. And so this is a family where n is greater than equal to 1. As I've said, lambda is a measure which is supported on this curve. Let me just write lambda there to remind myself where it lives. And then the game is that we move it around. So this is when I use the notation that f star, for example, of lambda, maybe f to the k of lambda, is going to be another measure. And it's another measure defined by looking at subset B. So B here is just going to be some other Borel set sitting inside the manifold. And then I just take the set, I pull it back, and I measure it. So I pull it back to f minus k of B. It's another Borel set. And I just take the measure with respect to lambda. So one way to think of it is that I have this yellow curve, which I will now extract from my picture and draw up here in some sort of celestial way floating up here. So this was where lambda lives. It's going to be this curve W epsilon U X. And what I'm doing is I'm pushing it forwards and it's getting longer due to the fact that it's in the unstable direction. And it gets awfully long and it wraps around the manifold. And you can see that the support of this image measure is going to get denser and denser and denser. But what actually happens is that it converges in the following way. So then, in fact, the sequence of measures mu of n converges to our friend the SRB measure as n tends to infinity, and it converges in the weak-star topology. I.e., you integrate against your favorite continuous function and the integrals converge. What?
Minus KB. B is where? M?
Now, B is inside M, that's right. So here is my set B, and I want to know what its measure is with respect to the push forward of it. I'm taking the pre-image of the set B to move it back to somewhere down here, I guess.
And then it becomes longer and stable direction.
It will do, but I'm just when it's not living, when it doesn't intersect this curve, well, it will probably look widdly. I'm not sure I could do widdly, but widdly looks like a bit like that. So then I'll be looking at the measure of these bits added up. I guess. That's my plan anyway. Well, my notation just tends to be surprising on occasions. Not always accurate, but sometimes surprising. That's what it's meant to be, yes. Yeah. I mean, I tend to keep track of where things are going by virtue of the fact that I think about where the supports are. Hello.
Well, you can start from any point X here.
Yes, you can start from any point X here. The reason being that since it's a transitive and not soft diffeomorphism, these unstable guys, they wind around densely. The foliation is minimal. It's just like on a torus. If you think of a linear toral automorphism, then the unstable directions have got irrational slope, they wind around irrational slope. It doesn't really matter where you start from. It works much better when you start quickly. It really doesn't matter where you start. Anyway, so there's some theorem like that due to Sinai. And so that constructs the particular equilibrium state corresponding to this particular potential, giving this definition here. So a question that one might ask, if one was minded to do so, and the question is the following question. How can we generalize this to other potentials, G and C, alpha and beta? Not just phi, but some other guy, which actually rhymes. Okay, so that's the question. And the answer is, well, you can do it in various ways. Let me mention two, one briefly, one less briefly. So how are we going to modify this construction if we want to get some other measure? And what are we going to rub out next? That'll be a good question. How the example can go. Okay, so how are we going to modify this construction if we want to get the potential? So if we want to get the measure associated to the different function G. So, sorry? Great. Why don't I get as far as stating the theorem, which is about five or six lines, and then I'll take a break. How's that? Okay, so there's one approach. That was my break. Was one approach. Second break. Due to Climenhaga, Pesin, and a name I can't pronounce, but maybe many people here probably can. And the game there is that they replace the measure lambda, the volume on the small piece of unstable manifold, by some other measures, which of course maybe lambda of G, which is going to be singular with respect to lambda. And a second approach, which is the one I want to state in a moment, is the following. So another approach is to consider a family of measures sitting on this piece of unstable manifold. So instead of a single lambda, I get a family. And so another approach is to replace lambda by a family lambda n. And these guys, lambda n, they're going to be equivalent to the volume, but they're not singular. And in particular, the formulation is the following. So this is the result by a student of mine, myself, which basically says that if we're given a function g, which is going to be our nice function for which we can associate an equilibrium state, could be phi, could be something else, and then I define lambda n on the a piece of unstable manifold, and I define it by well, these measures are all going to be equivalent to the volume, so I may as well define the radon-nicotine derivative. And the radon-nicotine derivative is just going to involve the exponential, so it should involve this function g somewhere, and indeed it does. So we sum k equals 0 to n minus 1, and then it's g, but we have to take away the other potential. And we sum this along the orbit. Let's propose back to the k. And then we normalize it, which means that we integrate over this piece of unstable manifold some expression looks like the thing above, and then this works for the way it's defined. Then I've run out of space for the statement. Let me erase part of the question, maybe all of the question. And the conclusion is going to be that we do the same thing. So then if I look at mu of n, which is going to be the average of something, k equals 0 to n minus 1. Well, in the Sinai result, he was just averaging a fixed measure. So here what I want to do is to push forward my families of measures. So this will be, here's an n, it will also be an n, it's a k. Then the claim is that this converges to, well, in general, it's going to converge to the equilibrium state as n tends to infinity. So it converges in the Wickstone topology as n tends to infinity. Okay. Maybe a break time, what do you think? Okay. So after the break, I will make a few comments and then I will move on to talking a bit about pressure and stuff. Whatever that is.
10 minutes.
10 minutes late.
Sure. Okay, thank you for coming back. Now, let me just conclude what I was saying in the last lecture by making a couple of comments. One is that it's meant to be like a generalization of Sinai's theorem. So if I had taken my potential G to be equal to phi, the one that Sinai would have liked, then in fact, the sequence of measures all becomes constant. And so you get exactly the same result as Sinai. So it generalizes it in that sense. Perhaps a few years later than he actually did his result, of course. And the second comment is that, well, I didn't say much about the proof. There's some hints in the online notes. You might have thought, for no particular reason, that it uses Markov partitions and transfer operators and stuff like that. But in fact, it doesn't. What it does is it uses just some ideas from the proof of the variational principle due to Zelerowicz. Proof of Zelerowicz. So it uses an inequality from there and it messes around a bit and it's quite direct. So it's actually quite general. So the same method applies without too much difficulty to things like hyperbolic flows, Nosov flows, that kind of thing. And you'd hope it would apply without too much difficulty to partially hyperbolic systems, but you have to start imposing some conditions to get things to work, such as life. Anyway. So what I wanted to do in the remaining, whatever it is, 5 minutes-ish, is I thought maybe I would talk a bit about subshifts of finite time, which hark back to what I was saying in the beginning about sequences and statistical mechanics. But of course, they run in parallel with ideas about hyperbolic dynamics because subshifts of finite time are like abstractions of these kinds of hyperbolic systems. So let me just give a quick definition. So here it goes. So definition. So again, I want to have some space and I want to have some dynamics. And so let me begin with the matrix. So A is going to be a K by K matrix. K is just some finite number greater than or equal to 2, natural number. And it has entries either 0 or 1. Why not? So as I just said, K, I'd like to be at least 2, otherwise it's not very interesting. And then the appropriate space is going to be the set of infinite sequences by infinite, so there's going to be xn, and runs from minus infinity to plus infinity. And how do they go? Well, they're going to be just sequences of values 1, 2, up to k. So that's my set of possible choices for my infinite family. And this matrix A just imposes some conditions about nearest neighbors. So this just says that A of xn plus 1 should be equal to 1. And this should be true for all natural numbers n. I want to say that this is equal to 1 for all n in Z. I said natural numbers, I should have said integers, it's two-sided shift. So the space itself is just sequences of digits 1 up to k. And if I didn't impose any condition, it would be all possible things. But in fact, I'm going to impose a condition that there's a nearest neighbor condition based on this matrix A. Of course, classical example would be I could take A to be equal to 1, 1, 1, 1. And then in that case, sigma of A would just be all sequences with a start 1. 1 or 2 raised to the power of Z. Very exciting. And then we can define the dynamics. Dynamics is going to be the shift map, which for some reason I always write sigma. This will take the sequence to a sequence. And the way it works is it just shifts sequences one place to the left. So the shortest possible way to write it is probably to say that I take a sequence, I shift it, and I look at the nth place, and then it should look like the old first place. But basically, it just takes sequences and shifts everything one place to the left. And we can also define a metric on this space. It's got a nice topology already from the Tikhonov project topology, but we can define a metric anyway. And so we can define that I'm given 2 infinite sequences, x and y. X looks like this, y looks kind of similar. Then it's going to be, well, if x is equal to y, oops, wrong way around, it should be equal to 0 if x is equal to y, otherwise it's not a very good metric. Otherwise, it's going to be at some distance that gets smaller if the sequences agree for a long number of places either side of 0. So an attempt to write that would be when x is not equal to y, and the value of k here is going to be k dependent on x and y, and it's going to be, maybe it's going to be the infimum of the absolute values of the n, such that xn is not, I'm not so sure I like this at the moment. This is maybe where it's where xi is, it's a supreme, yi, so let's say for I equals, yes, I should have thought about this a bit more before I started writing it. I want to agree for so many places either side, so I want to take the maximum of the values of n with the property that they agree for, I guess, I less than or equal to blah, 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 blah. Something a little like that. So sequences that agree for a large number of places either side of 0 have the property that they're close. Okay, so something along those lines. And so as before, we now have a dynamical system. So we have a space, we have a shift, and we also have shift invariant measures. And so as before, we can define for a function g. So g is going to be a Holder continuous function, this time on my sequence space with respect to this particular metric. And I'm going to define for this an equilibrium measure and pressure. And the way I do that is that the equilibrium measure, which I should have called something at this stage, is going to be called mu of G, and the pressure function, which will be called E of G. And the way I define it is as before, which is that the measure is the one which maximizes the entropies plus the integrals with respect to all possible measures. So this is the entropy plus the integral for this guy. And this is going to be equal to the supremum over all. Mu is going to be a single invariant measure, probability measure. And again, it's just the entropy plus the integral of G d mu. So everything I said before for a Nossoff system has now become for subjects of finite time. It's a symbolic system modeling this particular guy. And the pressure here is just this value. This is the pressure of U, it's just a number. Okay, so as you might imagine, everything I said previously about constructing equilibrium states, blah, 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 would also apply in this case. With suitable modifications, we have to understand what it means to be a bit of unstable manifold, but that's not particularly difficult. But what I would like to do instead is to talk about another class of problems which are to do with what are called rigidity and flexibility. Requires me being able to spell these words correctly, of pressure. So this is a class of problems that were kind of interesting some years ago, and then they fell out of interest and they came back again. So let me say something about that. And so what does rigidity and flexibility mean? Well, in analysis, or possibly geometry, depending on the viewpoint, there are old problems about what information you can get on a manifold from lesser information on, say, a spectrum. So there's a famous problem due to ants, which is, can you hear the shape of it right? Well, it simply means that if you have, for example, a surface, which I can draw, it doesn't look like a potato, almost. So you have a surface, and you look at the spectrum of the Laplacian on this surface, and does it tell you what the surface is? And the answer is no. There are results by Marie-France Vigneras and other worthy people who showed that it was possible to find does the knowledge of the spectrum imply what the surface is? And the answer is no. But it does give you some information.
When you say what the surface is, you mean the Riemannian metric?
That's correct. So in the case I was talking about, there would all be Riemann surfaces. And the question was, if you know all the eigenvalues of the Laplacian, does it determine the Riemann surface up to isometry? And the answer is no. You need more information about where. Well, you need more information, basically. But I'm not a geometer, so I'm kind of bluffing that bit. So let me just put a bullet point there. But then more recently, there were dynamical formulations of rigidity and flexibility questions, which came from the work of somebody I also can't spell. There we go. He was, I think, a top class student. And they have dynamical questions. Along the lines of, can you construct examples of Nossoff diffeomorphisms which have the Lyapunov exponents that take certain values, whose topological entropy is some other specific value and whose metric entropy is some other value, subject to whatever constraints exist between these various values. So they're along those general terms. But I want to talk about another question, which is not exactly in this ilk. I mentioned it mainly as some sort of motivation, but the question is, if you know some information about this pressure function, What does it tell us about the function g? Well, at the moment, it doesn't tell us very much because it's a single number. And lots of different functions g are going to have the same number. But we can look at a sort of parameterized family of these things. So here we recall the old problem on pressure. And this says basically the following. I haven't got around to saying what the problem is yet, but let me just say here is some notation. So let's assume that I'm given a Holder continuous function g. So this is going to be a Holder continuous function on my sequence space, just because it's a convenient place to work. We can find a map, which I will call P subscript g, and this is going to map me from maybe the positive reals into the reals. And the way it's defined is that I take a number t and I map it onto the pressure of, I take the function g, it's just the Holder continuous function defined on my sequence space, and I multiply it by t. And so I get some sort of plot. So this is meant to be t, this is meant to be the plot of the function, and so it's going to look like however it looks. Possibly it doesn't look anything like this. Let me try to draw some function that looks like it should be something. So the idea is that I take a particular value of t, possibly not using the same color chalk, and so this would be p of t times g. So just knowing pressure of g, a single number tells me nothing. The question will be, if I take a parameterized family, I just keep scaling these guys. Well, as g increases, p of t does not increase linearly. It has a nice curve to it. And then you get a family of curves. And in particular, there's a bunch of properties. And it has this function as some simple properties, which are kind of well known, but let me say them anyway. So first of all, the function pg of t. So for any Holder continuous function, I get such a guy, and this guy is mapping me from the positive reals onto I guess the reals. And it's actually going to be a real analytic function. So it is real analytic. So let me write maybe EG. So if you don't like real analytic functions, it's smooth, but better than that. So, and the proof of this is due to Ruel, who showed that in this case, e to the pg of c is an eigenvalue. It's an isolated eigenvalue. Is an isolated eigenvalue for some operator or a constant operator. The cousin of the matrix that appeared at the beginning, except this cousin now acts on functions, not on two-dimensional spaces. I keep changing my tool until I find what I like. Not this one. If I transfer operator and then uses perturbation theory. Perturbation theory tells you if you change the operator, then isolated eigenvalues change in a nice way, in this case analytically. And so in particular, when we change t, it changes the operator and this maximal eigenvalue changes. Some stuff like that. It's a cute proof. But it tells us that this curve is as smooth as you would like, in fact, analytic. And the second one is if you look at my picture, it's meant to look like the curve is convex. And the reason is the curve is convex. And so PG of T is convex. And this was also proved by Ruel. And the way he proved this was to show that the second derivative was greater than or equal to 0. And so in particular, when you take your function, you look at the second derivative at some value t, then it has some particular expression. One expression is you can sum n, it's an element of z. It's going to be a factor of 2 out somewhere. G composed by shift to the power n times g is mu of P of g. I have to take away the integral squared, the mu T of g squared. So I'm looking at these terms, I'm summing them over n, and then what should happen is I get something finite, but in fact it turns out to be positive because you could rearrange this if it's the same as the limit n tends to infinity of 1 over n, the integral of the summation I equals 0 to n minus 1 of g components sequence I, who my indices match up, minus n times the integral of g, the mu times t of g, so it's the equilibrium state for this guy. And then we square this guy, and this thing, you can see is positive because everything inside is positive. So to get from there to there is just messing around with calculations, but that's what the formula says. So in particular, it's a positive definite expression. And the third property, which I will squeeze into here, says that if we let alpha be bigger than 0, so we choose some value down here, is alpha, then the tangents to the function here, g, which are restricted to alpha up to infinity now, intersect the vertical axis into the set. Vertical axis in a closed interval. Which for no particular reason I'll call BC. So this is meant to be sitting inside 0 to infinity, something like that. What it's meant to mean is that if I'd drawn it a bit better, which I didn't, was that if I look at all these tangents up here, so this guy goes up to say alpha, here's a tangent line, here's going to be another, oops, very well drawn, another tangent line down here. You can go along with the different values of t, the different tangent lines up here. And had I drawn it remotely, well, then what would happen is that all these tangent lines would have to intersect in some closed interval here. Okay, so these are 3 properties that you get by taking any Holder continuous function you fancy and then associating this pressure function and then looking at the one parameter family associated to that. So there's 3 properties of this guy. And so a question is, well, if I give you a function which has properties 1, 2, and 3, does it have to be the pressure function for a particular Holder continuous function G? And so these sorts of questions have been hanging around for some period of time. And so the latest manifestation is the following. Let me give an attribution. So here is the question. The question, and it's due to Durango and Force. And it says, well, let's let alpha be greater than 0. I'll explain why the alpha is occurring in a moment. So if the function let's say m from alpha to plus infinity into R satisfies properties of 1, 2, and 3, then does there exist a function g, a wholly continuous function in my space with the property that that's what it is. So does there exist such a function g, wholly continuous, oh, too many alphas, aren't there? That's interesting. Let me call this beta then. It just means wholly continuous functions. Does there exist a whole continuous function with the property that the associated function pt with g, that is the pressure function associated multiplying g by t, is actually going to be equal to the function we were just given, which was possibly called f of t. So for all t. So it's greater than alpha. And so this is the question that was posed. Why has this alpha started appearing? The reason is because you don't really want to look at the pressure function evaluated at 0, because when you take T to be equal to 0, you get the pressure of 0, which is the topological entropy, which has to be related to algebraic integers. So it imposes an extra condition, which we're just skipping. So basically, we're just taking these three properties of some sort of function. So given any analytic function, with the property that it's convex, it's real analytic, and it intersects its axis in not too big a set, then can we find a Holder continuous function g? Well,
So you fixed that.
sorry?
You fixed that. In the question, A is fixed.
No, A. Well, yes, A is fixed here. Yeah. I was slightly worried that the A was back to the Holder exponent. Yeah, so that doesn't matter quite so much. So let's choose any alpha greater than 0.
The subject of finite type is fixed.
The subject of finite type is fixed as well.
Could be a different question.
It could be a different question for different subjects of finite type. No answer at the time was known for any subject of finite type. So it's kind of wide open in that sense. But then there was a result due to the same guys. So here's the theorem. And let me abbreviate it to KC. So and they prove that if a function f from alpha to what's infinity mean? So R satisfies 1, 2, and 3, these three properties, then there exists then there exists. What does there exist? There exists. Then there exists. To read. What does there exist? Well, there exists a Holder continuous function. No, they don't. A continuous function. Sorry, I got carried away. A continuous function. Not a Holder continuous function, but a continuous function on a full shift. Some full shift. Such that the result is true. So that's f of t is going to be equal to the pressure of g of t. So it's a sort of answer, except it's not dealing with Holder continuous functions. It's looking to a much bigger class of continuous functions. So if you give me a nice function f, which has these three properties, then their result is saying that they can find a continuous function which has this particular property. But the pressure function has this nice shape, satisfying these three hypotheses.
I have a question.
Hi.
So assume we have a function capital F, which has a form at alpha over 2. So I suppose it still can satisfy properties 1 to 3, right?
I guess, yeah.
It doesn't. So doesn't it contradict to the properties 1, 2, 3 of function PG? So
Yeah.
the theorem states that there exists a function PG for such f but that should be defined on the form R plus.
Well, the function is defined, but we don't know anything about its properties beyond the interval of interest between alpha and plus infinity. I mean, they're constructing an example of a continuous function, but we don't know that the pressure function PG of T is going to be analytic outside of where it's shown to be analytic.
So PG does not need to specify actually the properties 1 to 3 on the whole positive real line.
Right.
I think.
Yeah, so if we knew more about it, it would be possibly helpful, but in fact, we only know what's fitted to that particular curve. So they're really working with continuous functions using some construction. But they're saying that if you look at the wider class of continuous functions, there exists a continuous function called G, which is going to be continuous on the subject of finite time, with the property that its pressure function matches up with this guy on that particular domain. So for the inside, where am I saying? Alpha to the plus infinity. But it doesn't say much about Holder continuous functions. But in the context of Holder continuous functions, you can do a bit more. Because when I stated that Ruel proved convexity by looking at the second derivative, well, you get an explicit sort of form for the second derivative in terms of these guys, which are called correlation functions, and other expressions. And if you try to look at higher derivatives, then you can do that as well. So if you're given a Holder continuous function, and you look at the associated function PG of T, and then you look at the third derivative or the fourth derivative or the fifth derivative or something like that, then you get rather complicated expressions, but expressions which are quite manageable. So, for function G in C alpha sigma A, then there's the following result. So this is a theorem due to Chinese guy and myself, which says that, well, for G, it's elements of C alpha sigma. So here, sigma is going to be a bullshift, meaning all the entries in the matrix A are equal to 1. And it's a Holder continuous function. I'm going to go back to writing beta just in case the answers reappear. And it says that there exists a constant M, which I will call M of G, because it depends on G. So there exists a constant which is positive, with the property that for any T greater than 0, if you look at the square root of 2 pi cubed, and you look at the second derivative, my function PG of T, which is actually written down here, but I raise this to the power of 3/2, and I multiply it by the absolute value of the third derivative of this guy, 3, G of T, then this is going to be less than something, and the something involves 9 times the third derivative, so this is PG 1, 2, 3 of T. And then if you look at twice the fourth derivative, so at some stage I should put the numbers in brackets, but maybe I'll just write 4 dashes. So we get this expression, plus another term, which is going to be 3 times the square root of 2 pi cubed. The M now appears, and then this will be PG, and I think it's 2 derivatives, T positive, power 5 over 6. Okay, so there's some complicated looking expression that you get for any Holder continuous function, at least on a full shift, which simplifies the expressions a bit. And it relates the second, third, and fourth derivatives of the pressure. So before we were asking, well, if we have a function which has certain properties, convexity, analyticity, and some other intersection property, then does this, can this always be realized? And the answer is going to be significantly no, because there are more conditions that are hidden on the properties of the pressure. So in particular, that's the end of the statement. In particular, this imposes extra conditions on FT in order for it to be realized, or it. Sorry, the G. Sorry, what was it?
Last important is this S.
Which one? This one. That's a 5. My 5's like that. I managed to cross my 7s. It's not the only thing I ever managed to do that makes it better. But that's meant to be a 5, yes. So there's no absolute values because the second derivatives are all positive, except when I have third derivatives and possibly fourth derivatives, when the sign is a bit more ambiguous. And so it's just some complicated expression. How do you get these complicated expressions? You just do the same sort of thing that Roel did in order to get his second derivative formula. He's got some tricks involving transfer operators and messing around with things. And you just keep doing it. You just keep differentiating away happily. And then there are relationships between the expressions that you get. And this is one of them.
It's taken by physicists, Pollicott and other people, when they give also inductive procedure.
They do, yes.
Somehow important.
Sorry?
You know that M somehow important for other.
No, M is just there because there is a constant that one has to deal with.
P square root of 2 pi Q. There's gravity on the other side. Why doesn't it fit into the M?
This one.
No, the 3 times.
That one.
Yeah.
What would you like me to do?
Well, it's all inside M.
I could do that, yeah. Let me say, let me introduce M prime. Well, okay. Let me say yes and not change anything. How's that? Yeah. So the point is that if you're familiar with the formulas for these different derivatives of pressure, the idea is that you take some sort of transfer operator and you look at some maximal eigenfunction for it, and then there's an E for the pressure, blah, 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 blah. So there's some expression like this. There's an operator, and you get this guy, and then you start differentiating away happily. And the difficulty is that as you differentiate more and more times, you end up with lots of derivatives of this maximal eigenfunction. And the M is just a bound on the contribution from these guys. I'm not sure M is a particularly good choice for a constant anyway. So this imposes extra conditions. So for example, we cannot f of t equal to some expression. So the one I've written down is twice t squared plus 3t plus t e to the minus, would you believe, t squared? And adding to this e to the minus t squared. So this is a function, especially when I divide it by something, which is t. So if I took my function f of t to be this expression, then the claim is that it's analytic, which I kind of believe. It's convex, which I'm kind of happy to believe without checking it. And it also has a third property, but it can't be realized by a pressure expression. That is, we can't find a function g with the property that the pressure of t times g is actually equal to f of t, because it doesn't satisfy the corresponding identity here. As t goes off to infinity, this constant n doesn't help us enough, that sort of thing. So anyway, that's just an application of some messing around with this sort of pressure function, which addresses a question of these guys. Okay, so I wrote those notes yesterday, and so that was, of which they consist of 7 pages. I noticed if I turn the page, I start getting into Christian Bonatti's lecture. So unless you want me to repeat that one, I will maybe stop here. Thank you very much.
The last 2 theorems, I guess, were about the full shift, right?
Yes.
Do you have some counter examples for the case and you have assumption?
I haven't, well, we don't have in the sense that I can actually give a counterexample. I mean, I see no reason that it wouldn't work in that case. So the reason we're looking at the full shift is because despite the complexity of the expression, it would be worse if we had a subshift of finite time. If we had imposed extra conditions with the matrix A. So for a full shift, life is easier, which is why it's of this form. And since we were interested in finding conditions which were obstructions to this general problem, we were quite happy just to work with subshifts of finite type. It might be that by some magic, there is some subshift of finite type where the original question might be, you know, have a positive answer, but I think that's kind of unlikely. So I haven't really thought about it.
For the collection of things, is it open? What's the topology of the set of things for which you can solve the problem? You get information for quality.
What a brilliant question. I've never thought of that. I could bluff an answer, but I'm not sure I'll manage it.
I mean, it's clearly not generic.
No, that's true. I don't know. I mean, so people who study pressure a lot tend to, you know, they tend to stop at convexity and analyticity. And so I don't know that it's been studied in this sense before. The only people I know who have looked at higher derivatives were Catanian and Sinai, but they were just interested in generating functions and stuff themselves. And there are people who are interested in higher derivatives because they're related to different kinds of statistical properties, like beyond central limit theorems, the other kind of higher moment stuff. But now I'm at the waffling stage. I'm just saying that there are some people that study these things, but I am not one of them, so I don't know very much about it.
That's some conditions that there are other conditions.
I should imagine so. I mean, if you keep taking higher derivatives, I suspect it would just get worse. I would imagine so, yeah. But I mean, I don't think I have the time to do a countable family by myself. I need students to do that.
I have another question. In the theorem of Kucherenko-Kouas, is there a chance that for some subfield it will be false? That is, there will be, for example, one you will not be able to find even a continuous function.
I don't know. I'm not that familiar with their proof. I looked at it, I read it, I didn't really understand it all that well. I don't know. My impression is that they're looking at full shifts for the same reason, that it's more convenient to do that, because it's also quite technical. So I don't know the answer to your question. I suspect that, you know, if you were pathological enough, then maybe you could cause problems with these constructions, but I can't guarantee that. I mean, if you wanted to be really pathological, you could just take a matrix where there's just a single point, which wouldn't really be very helpful. But I really have no, beyond that, I don't have any insight.
More questions?